our conversation about mathematical proof starts off by considering several mathematical statements. These are statements of the form if P of n, then Q of n, that are proposed to be universally true. That is, we think that these are statements that may or may not be true for all, in this case we're limiting ourselves to the domain of positive integers. So the first part of the exercise is to take a minute and decide which of these statements you think are universal truths and which ones are not. But more importantly, the most important thing here is to get my pen. The most important thing here is to pay attention to the examples that you're considering when you give your answer, because it's the point of view that you take as you're considering these statements that's important for the way we're going to write mathematical proofs. So take a couple of minutes to decide this, and I'll then restart the video. You could pause it here. Okay, so I think that probably you all believe that this statement was true. Hopefully you tried examples like 15, 25, and so on, to 35, and decided that this always works. You may not have even tried any examples at all. You may have just said, I remember that my third grade teacher told me this. But we believe this is a true statement. On the other hand, we say if a number is divisible by 2, then it ends in 2. You may try numbers like 12 that are divisible by 2, and they do end in 2, and you're feeling pretty good about it, 32. So all of these seem okay, and then somebody suggests, well, what about 14? And you realize that 14 does make the hypothesis true. It is divisible by 2, but it doesn't end in 2. So 14 is what we call a counterexample to the statement, and so that would be evidence that the statement is false. And of course, there are lots of other counterexamples. So when we say a statement is true, like we did for the first one, what we mean is that you will, if you keep trying examples satisfying the hypothesis, you're never going to come across something that makes the conclusion false. That's what you're never going to see that. So the third, fourth, and fifth statement, I believe you'll find that you will not find a counterexample to, but what I want to keep track of here is the examples that we try. So for number 3, you might try 1 or 7 or 3 or 13, and you're not finding any examples, so you would say, well, I think this is probably true then. But notice that every example you're trying numbers that satisfy the hypothesis, and then for each one, you're checking to see if the conclusion is true. Similarly, for number 4, you might try 7 or 11 or 23. You're trying examples that satisfy the hypothesis, and then for each example, you're checking the conclusion. Right? But you're not really considering the conclusion as you pick your numbers to check. You're only considering the hypothesis, and then with that example, you're checking the conclusion. So just be aware of the way you're thinking about it. So we believe this is also true. And then similarly here, you might try perfect squares like 9 or 16, and you'll find that you will not find a counterexample to that either. And so we believe that's also true. Now, what we want to get at in this section is when we say it's true, we don't really know it's true. What we're really saying there is, I was incredibly lazy, and I tried 3 examples or 4 examples, and I couldn't find a counterexample. So based on that evidence, I think this statement is true. What we want to get at in this section is, if I believe something is true, can I explain why? Can I actually prove that the statement is true? So the way we're going to write our proof is we're going to take the point of view that a proof is a correspondence between the author of the proof and the reader of the proof. The thing to keep in mind is that the person reading the proof is playing exactly the same role that you played in the previous exercise. So when you did this exercise, you were pretending to be the skeptical proof reader. So that means that we know the position that the reader is taking. The reader is hoping to find an example that makes the statement false. But to do that, the reader is picking examples that satisfy the hypothesis, and then for each one, checking that to see if it satisfies the conclusion. So that's the process that the reader is going through as they're searching for a counterexample. So we can take advantage of that and write an argument that intercepts that process and tells them why, in that process that they're already using, why they're not going to be able to find a counterexample. So here's an example. This is the 5th statement that we had a minute ago. For every number bigger than 4, if your number is a perfect square, then n minus 1 is not prime. Notice that I turned this into a nice if-then statement, and the reason I did that was so that I could talk about the hypothesis of the statement and the conclusion of the statement unambiguously. A lot of times people will present statements or ideas in mathematics where they don't really say the words if-then, but somehow they're implied, and that's a little bit of what we were talking about in the previous section, and that's why we went through those exercises of translating English language statements into statements with formal logic. So here's the idea. When the reader is considering this statement, this is the skeptic, or this is the person we're writing our proof for. The skeptic is choosing numbers that satisfy the hypothesis, and then for each one, checking the conclusion. And so I don't really know what order they're going to try these in, or what rhyme or reason they're going to have to it, but I know that every n that they mention is going to be a perfect square, and then for each one of those, they're going to subtract 1 and check that result to see if it's prime. So here's how we can intercede in that process. First we need to make sure that the author and reader agree on the definitions. So let's make sure that the two words in this the two words in this statement that are math words are perfect square and prime. And so we'll make sure that excuse me. We'll make sure that those two words are clear. So a perfect square means that you are the square of some whole number, right? So the fact that m is an integer here is extremely important. So when we say n is equal to m squared, that's fine, but we need to say that m is a whole number, because being a square of something is not impressive. Being the square of a whole number is impressive. And then for primes, we typically just eliminate 1 from being considered at all, so we don't have to get into an argument about the semantics. And then we'll say that a number is not prime, or number is prime if it cannot be written as the product of two numbers both bigger than 1. So for example, 6 is not prime because it can be written as a product of 2 and 3, neither of which are 1. So our point of view will be the author of the proof. We're going to write this as a correspondence to the reader, and we envision that the reader is actually going through this process that we went through as the skeptic. And the reason we write this as a letter is just to remind us that that you really are a person writing words for another person to read and as instructions for the other person to follow. And so by writing it as a letter, it's a little easier to envision that you are actually writing to a person who has to read this and do something with it. But here's the exercise I want you to go through. It's a bit like a magic trick. I want you, and I really do want you to do this, I want you to write a perfect square number greater than 4. Obviously you can't tell me what it is because you're not really in the same room with me. And I want you to write the number n that you picked, the perfect square you picked, on your page. So you should be writing on your page n equals, and then write a perfect square there. Now I have no idea what perfect square you picked, but since you promised that it was a perfect square, I know that your n is m squared for some number m. So in other words, if you picked for n 25, then your m is 5. If you picked 49 for n, then your m is 7. So if you agree that n is something squared, you must know what that something is. And I want you to write that down here. I want you to write m equals, and put here the number that, if you square it, would give you this number. Okay, so you promised that n was a perfect square, so you must agree that there is an m like that. Okay, and again, I don't know what your number is, but I do know that much about it. The next part is, and this is part that seems a little bit like a magic trick, I want you to write down, you have a number m on your page, I want you to subtract 1 from that, and that'll give you another number, and I want you to add 1 to your m, and that'll give you another number, and then I want you to multiply those two numbers together and write down the result. And again, if you need to pause the video, if you need a calculator, if you picked a large number, then go ahead and pause the video to do that. Now, what you should have noticed is that the number that you wrote in this blank is exactly 1 less than the original number that you picked. And at first, this seems like some kind of cheesy magic trick, but really this is just algebra. And it makes sense that it's algebra because you are doing arithmetic with numbers, And we know that the way to capture arithmetic with numbers as general statements is by using algebra. In other words, you know what your m is, so you can use numbers. If I don't know what your m is, I would be stuck with algebra. So the algebra would look like this. I'm saying that if you multiply m minus 1 times m plus 1, and again, now I'm not thinking of m as being your number, I'm just thinking of it as being the variable m. So from my point of view, since I don't know the number, this is all I could do. If I use FOIL here, I will get m squared. Now there's going to be a plus m and a minus m for the outer and inner of FOIL, and those are going to wash away, and then I'll have this. So m minus 1 times m plus 1 is really m squared minus 1, and of course m squared is n. Right? That was the whole point. And so it's not magic that m minus 1 times m plus 1 is n minus 1. It is just algebra. So back here, I now can just explain to you, and again, I don't know what your number is, but I can say that on your page, you now have the number n minus 1 written as the product of two smaller numbers. In other words, it's written down as two numbers that are neither of which are 1. And so, therefore, what you have on your page shows you that your n minus 1 is not prime. Now, since I didn't even have to know what your n is in order to make that conclusion, that means that no matter what n you started with, the conclusion would be the same. And so if you follow this process, you'll see that you'll never find a counterexample to the statement.